I've been using a bootleg version of the process real-world engineers use to conceptualize, build, and maintain complex systems to build stuff in Minecraft. Has it worked? Well, yeah, I followed the steps and we came up with some pretty decent stuff, I'd say. But did that process actually end up improving the final product? Yeah, that's up for debate. Today, we're not going to be building or designing anything, but we'll be doing some engineering all the same. Welcome back to... In case you're new here, yeah, we're actually trying to apply real-world engineering principles to Minecraft. Of course, if we just went off some uni textbook, nothing would make sense because, surprise, surprise, engineering processes are not made with the old block game in mind. But... and I'm going to give free will some credit here, we can do what we want. I made some slight adjustments to an already broken up version of the initial process, and I'm starting to feel like we might be drifting here. So before we get to any designing of super smelters and autocrafters, spoilers for next week, I'm going to clean up this process once and for all. We're getting a bit deeper into the theory here, but at least this time we have some examples to work off of. I hope you'll stick with me for this one, because I find it incredibly interesting. If you don't really care and you're just here to see me fail to understand redstone, there'll be plenty of that next episode. So I hope you'll at least be coming back for that one. I'm going to throw a reference up on screen here. What it's showing is the research paper I'm going to be referencing for the rest of this video. It's a literature review by David Wynn and Wynn Clarkson, and what it considers is three broad categories of what they call DDPs, or design and development processes. They review what to me felt like hundreds of different approaches to design and development, otherwise known as engineering, and I'm going to try to just point out a few things that stood out to me. In this paper, they consider three types of models: micro, meso, and macro. These are basically just words that mean how far you are zoomed out from the actual problem. A good analogy I heard is that the micro level is the Google Street View, the meso would be the top down of a city, and the macro level is like the map of a whole country. Now remember, the specific problem that we're trying to solve is still on the level of a single street. The meso and macro levels just consider the environment around your system context to a much greater degree. Now we need this to work for Minecraft, right? So stakeholder requirements, company budget, or the political climate just aren't really part of the equation. For that reason, we're going to be focusing on what the paper has to say about the micro level design and development processes. After all, we're not project managers or product owners, we're design engineers. We're the ones getting our hands dirty. Let me read you a passage from the Lit review. They find that all these authors prescribe the three main steps of analysis, synthesis, and evaluation. Analysis involves focusing on a problem and structuring it into a set of objectives. Synthesis involves generation of a range of candidate solutions. Evaluation involves the critical appraisal of those solutions against the objectives to rationally select between them and or to drive iterative improvement. I'm pretty happy with that. So let's get to finalizing a design and development process we'll be able to rely on indefinitely. As always, we'll start by defining the problem. I know I've said this a million times, but hold on. There's still some important things to think about here. What I failed to address in the past is the scope of each project. I mean, I mentioned it, but it was never baked into any of the steps. What we need to consider going forward is the system context. Say this is your Minecraft world. This is probably the most you can zoom out in our situation. We'll call this the environment. In this domain floats a bunch of stuff that may or may not matter to you. Now the thing you're building lives here. Let's call it the narrow system of interest. Everything inside the NSOI is the stuff we're trying to figure out. Say you need an iron farm. The farm itself is this thing. You can zoom in more into different functions and stuff, but everything in here needs to be designed. Everything in your world that will interact with your new iron farm lives in this outer bubble. We call this the wider system of interest. These things already exist, or they'll be designed and built separately. As the engineer, and this is a luxury mostly specific to Minecraft, you get to decide which elements live inside the narrow boundary and which live outside. You can put the autocrafter, storage systems, villager breeders, or whatever else you'd need outside the narrow boundary, and that leaves your brain free to focus on the task at hand, getting iron. Then once it's done, you can move on to the next element, and so on. Alternatively, you can also just move all that stuff inside this boundary and optimize accordingly. Though technically, you're not supposed to be touching anything that's in the WSOI, every element that lives inside here does need to be considered. You need to know what's going on out there in order to make informed design decisions in here. All these bubbles are what we call boundaries. And the whole picture will show you your system context. And it's the system context that will help us come up with our problem statement. For our bamboo farm, we put the bone meal source and the eventual endpoint, aka a super smelter, in the WSOI. We define the context so that we can work off the assumption that we can have loads of bone meal coming in and we need loads of bamboo blocks going out. That greatly simplified the thought process needed to come up with a solution. And it helps us to try not to sub-optimize. I'm not sure if this is still the case, but I wrote in my notes here in big letters, sub-optimization bad. Remember that all of this is just here to help you avoid to get stuck in design loops, where every change you make to the system requires 5 other changes down the line to make everything work. All we need at this point is a clear objective and clear realistic inputs and outputs. Now that you've defined a system context, you know what you have available as inputs, and you know what you're trying to output. Now, you need to come up with the logical steps required to get from A to B. If any action needs more than one word to describe what it does, you probably need to break it down further. Alright, it's not that serious, but you'll get a feel for what I mean as we go here. This isn't a step most veterans need to achieve anything, but it's 100% something they're doing in their head as they're going. You're also not going to be able to break every farm or contraption down like this. What's important is that you take the time to consider the logical sequence of events that need to happen to get the outcome you want, especially if you get stuck at any point. This will be your guide once you start building things. In real life, especially on bigger projects, each function can be complicated enough to require a whole team of engineers to design. So interface design is a big thing. Now, we are not a team of engineers, but then again, we also don't have to factor in physics and budgets. Either way, it's important to start considering how each module will interact with the others, which functions have what information available to them. You don't need to write anything down. Just take a second, think about it. It's worth it, I promise. At this point, we officially have a roadmap. We know what needs to be done to achieve our goal, so it's time to come up with a few different ways of achieving it. The traditional way of doing things is coming up with concepts for the individual functions and then evaluating them based on output, efficiency, complexity, lifespan, cost, etc., etc., etc. For our case, we know what each subsystem needs to achieve, so we can just grade every concept based on that. You're also not obligated to come up with more than one method, because in a lot of cases, there aren't really more than one way. A lot of these functions will have some interdependency as well, unfortunately. There are different strategies for dealing with that, but I'm not going to go over them here. This is another step where if you just take the time to come up with a way to make each individual function just work on its own, the final design is going to be so much easier. It's time to put everything together. This is the point of the project where the feasibility was confirmed, so now we need to fill in the details. In mechatronics, this is where you more often than not fall into a deep pit of despair because you just aren't good enough at interface design and now nothing is working as it should. Fortunately, the concept of capacitance doesn't exist in this game, so we're safe for now. This step is where you'll probably be spending most of your time, but hopefully all the effort we put into the first 3 steps was worth it. Now, a lot of design frameworks get weird here. IRL projects are a lot more complicated, but in Minecraft we don't need to worry about most of it. Something I did want to highlight is that an option you always have is to merge this step with the conceptual design. If you prefer working on the whole thing at once, come up with a few different complete concepts and consider their strengths and weaknesses. There really isn't one correct way of doing any of this. Just build your contraption. Hopefully it works. Personally, I like leaving it there, as you can see, but you owe it to yourself to look over what you've done with a critical eye and see what you can improve. Even just starting from scratch again can help you end up with a better design, or lead you to discover some mechanic or method you had previously overlooked. I'm not adding this as a step, not because I'm lazy, but because it's not really in sequence with the rest. It's a loop, right? Not really a next step. And that should do it. That's where I'm going to leave it. The last thing we need to do is put this whole process somewhere permanent. Yep, that's pretty much the best I could come up with. Kind of going for an old monument that's slowly being corrupted kind of vibe. Building is not my strength, so from here on out, hopefully we never have to make anything look nice ever again. But that's it. If you enjoyed this video and you're interested in engineering, please consider reading the paper by Wynn and Clarkson. It's quite informative, though obviously not to be seen as some sort of engineering Bible. I grabbed elements that were common between different methods, but there's no be-all end-all. Whatever works for you, works for you. I'm just trying to add some structure to my own thought processes. Anyway, thanks for watching. I'll see you guys later.